Hello everyone, you are hearing Omid Gheibi. Here I introduce a new version of the Voronoi game called Blind Voronoi game. First, let's see what the Voronoi game is. An and his co-authors in 2004 introduced it. The game elements are two players and a set of users distributed over an underlying space. The game scenario is the players alternatively place their facilities in the space up to a specified number of rounds. The assumption is each user asks service from the closest facility. So, what is the objective of each player? It is maximizing the number of users served by his facilities. Let's call it his payoff. We have an example here, a discrete Voronoi game on a line segment. You can see a set of users distributed on a line segment. It's a game in 2 rounds, and each player will place one facility in each round. For example, P1 puts his first facility there, then P2 places his first facility on the line segment, and here the first round is finished. The dashed line shows the perpendicular bisectors of the segment F to S. For the second round, P1 puts his second facility somewhere in the space. Finally, P2 finishes this game by placing his second facility. In this example, we can see the P1's payoff is 5 and P2's payoff is 8. Generally, through different settings of the following dimensions, we can define variant versions of the Voronoi game. These 5 dimensions are the number of players, the structure of the underlying space, such as line, tree, graph, 2D plane, and so on and so forth, the distribution of users, the number of rounds that the game will be continued, and the number of facilities in each round that each player can place. Here we can see some instances of the Voronoi game based on the specified 5 dimensions. For example, this is a game with 2 players on a weighted graph. The distribution of users is continuous and defined as the weight of edges or vertices. The game is in 1 round and the number of facilities can be asymmetric for each player. Here is another example. Players play the game on a square. The corresponding undercover area of the square to each player facilities Voronoi cell is defined as the player's payoff. The number of facilities for each player is the same, and the game will be played in 1 round. Also, we can see discrete Voronoi game on a line with a different number of rounds here. Also, we can see other variations that are mostly mostly about different spaces, such as simple polygons, graphs, and so on and so forth. One implicit point in all of these instances is the distribution of users, either discrete or continuous, is perfectly known to players. Now, what if players have imperfect information about users' distribution? Blind Voronoi game as an answer to this question. In this new setting, users' distribution is unknown to players. Only during the play, the distance of nearest users to the facilities will be revealed to all players. And it is applicable in real situation where players have no prior information about users' distribution. For instance, here we consider the 2 round discrete blind Voronoi game on a line segment. It's the same as a regular version of the game, except there is no information about users' distribution for all players. And players compete over the users in 2 rounds with one facility for each round for each player in each round. So how can we define a player's objective? As players are blind to user distribution, the objective should be independent of it. So players should follow a mixed strategy because pure strategy will not work here, as all the time there's a distribution for which the player's payoff is zero. We define the objective of P2 as maximizing the expected number of served users among all possible users distribution. And P1's objective is minimizing the P2's expected payoff. Now a question comes up. Why does not P1 desire to maximize her payoff? The short answer is all the time there is a dense distribution closely enough to the last facility of P2. Hence, P1's payoff can be zero all the time. Now, let's see the following strategy for P2. In the first round, places the first facility adjacent to P1's first facility. Here, adjacency means no user between two facilities. But how should players know the adjacency neighborhood? The answer is all players know the nearest users in each side of a facility, as we mentioned before. For the second move, select uniformly at random an open side of P1's facility. Here we have a strategy for the second player. Let's see an example. For example, P1 put his facility somewhere on the line segment. Nearest user on each side of the facility are shown by a red circle here. Now, based on the strategy, P2 select one of them arbitrarily to place his first facility. Here is the end of the first round. Now, P1 select his second facility on the line segment. Again, players know the nearest user on each side of the facility. Now P2 selects uniformly at random one of the three remaining candidate points. And the game is finished at this point. What is P2's expected payoff? As those four specified red circles cover the whole of the segment, hence the sum of n1 to n4 is equal to the total number of users. And we can show that the P2's expected payoff is 1/3 of n, at least. We just talked about P2's strategy. Now we can ask what P1 can do here. If you remember, we explained that P1's objective is minimizing P2's expected payoff, right? On the other hand, we found that P2's expected payoff is proportional to the inverse of the candidate points number. So P1 should increase this number, and his strategy is to not place facility adjacent to any other facilities. At this point, we have some main points about the suggested strategy. First, in P2's strategy, the four candidate points are an optimal set. It means P2 has an incentive neither to add more points nor to remove any point. Second, there is a strategy for the second player in the 2-round blind Voronoi game on a line segment that guarantees his expected payoff is at least 1/3 of all users. independent of the P1's strategy. The discrete blind version can be extended to higher dimensions. For example, in 2 dimensions, players will place their facilities on the plane, and Voronoi cells of facilities will determine the number of served user by each player. What about the player's strategies in higher dimensions? Like the one-dimensional game, every point where users may be located must be covered with some positive probability. Hence, the union of Voronoi cells of candidate points must cover all regions that may contain users. Let's see it in a graph. First, P1 places its first facility on the plane. Similar to the strategy in one dimension, suppose all players know the nearest user to the facility. Hence, we can draw a circle that all users are outside of it. Now P2 determines 3 candidate points on the circle such that their Voronoi cells cover all users on the plane. Okay, here we have an example. Like the game in one dimension, P1 moves first and places his facility somewhere on the plane. P2, based on the nearest user to the facility, determine an adjacent circle and 3 candidate points on it. Then select one of them arbitrarily and moves for his first facility. Here is the end of the first round. It's P1's turn to place his second facility. P2 follows the strategy and determines 3 new candidate points with the specified property. Now P2 selects uniformly at random one of 5 free candidate points. For example, here, 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 and here. And place his second facility on it. Here, for example, his second facility here. Here the game is finished. Now let's see the expected payoff for P2. To do that, we need to draw the Voronoi game of the 6 existed candidate points. Based on the we know that the sum of n1 to n6, because of the properties that we have explained before about the candidate points, the sum of n1 to n6 is equal to the total number of users. And we find that the expected P2's payoff is at least 1/5 of it. We can generalize this strategy to the following theorem, such that for a discrete blind Voronoi game in d dimensions, P2 has a strategy to obtain expectedly at least 1 over KD plus 1 proportion of total users. 2 previous cases are specific instances of the theorem. In sum, we introduced a new version of the Voronoi game by looking at the level of the player's information about the user's distribution. Our strategy can be applied to other versions of the problem, like the K-round and facility game. And as for future work, looking at the problem in other spaces, such as graphs and polygons, can be exciting. Okay, thank you for your time. Bye.